Welcome to the Bodhi Academy. My name is Amisha Kulaso, and in today's video we will continue with our chapter Solutions, class 12, chapter 1. So previously in this chapter we learned about ideal and non-ideal solutions that are present. Now in today's video we will learn about the colligative properties and determination of the molar masses. So previously we have learned that the vapor pressure of solution decreases when a non-volatile solute is added to a volatile solute. So this we have already seen that when a non-volatile solute is mixed with a volatile solute, its vapor pressure is going to come down. Vapor pressure of the whole solution is going to come down. Now there are many properties of solutions which are connected with this decrease of vapor pressure. Now this decrease is in turn related to many of the properties that are associated with this decrease of vapor pressure. Few of them are relative lowering of vapor pressure of the solvent, depression of freezing point of the solvent, evaluation of boiling point of the solvent, and osmotic pressure of the solution. So all these properties, they depend on the number of solutes that are solute particles that are present, irrespective of the nature of the relative of their nature relative to the total number of particles that are present in the solution. So this property is what we have spoken about. All of them, they just depend on the number of solute particles that are present. It does not depend on the nature of these particles. They can be of any nature, they can have any properties. Mostly it depends on the number of the particles that are present. Now such properties are called as these colligative properties. So now in today's video we will talk about two such properties. One is the relative lowering of the vapor pressure of the solvent and evaluation of the boiling point of the solvent. So relative lowering of the vapor pressure. So we have learned in section 1.4.3 that vapor pressure of a solvent in a solution is less than that of the pure solvent. Raoult established that the lowering of a vapor pressure, it depends only on the concentration. It depends only on the concentration of the solute particles, and it is independent of their identity. Okay, so we are saying that Raoult law said that a lowering of the vapor pressure, it is only happening because of the concentration of the solute particles and not based on the nature of the solute particles that are present. The equation given in section 1.4.3 establishes a relation between the vapor pressure of the solution and the mole fraction and vapor pressure of the solvent. So this we have seen in the Raoult's law, that this equation P1 equals to X1, that is the mole fraction, and P1 naught. Now the reduction in the vapor pressure of the solvent, that is delta P1, it can be given as delta P1 equals to P1 naught minus P1. Now this P1 we can write in this form of the mole fraction. So we write P naught 1 minus P1 naught and X1. Now if you see, we have these two in this equation, and here these two are common. So we can take it out and we can write 1 minus X1. Now we know that X2 can be written mole fraction total is equal to 1. So if you have to find X2, so it will be X2 will be 1 minus X1. So on 1 minus X1, that will be equal to X2. So delta P1 will be equal to X2 P1 naught. Now in a solution containing several non-volatile solutes, the lowering of the vapor pressure depends on the sum of the mole fraction of different solutes. Now when we are talking about a solution that contains n number of non-volatile solutes, in that case the lowering of the vapor pressure will majorly depend on the sum of the mole fraction of the different solutes that are present. So delta P1 upon P01 will be equal to P01 minus P1 upon P01, that equals to X2. So the expression on the left side of the equation, as mentioned earlier, is called a relative lowering of vapor pressure, and it is equal to the mole fraction of the solute. So this expression over here, this is known as the relative lowering of the pressure, vapor pressure, and this in turn is equal to the mole fraction of the solute, that is X2. So the above equation can be written as P01 minus P1 upon P01 equals to N2, that is we are talking about now the number of moles, N2 upon N1 plus N2. Since X2 can be written as what? N2 upon N1 plus N2, that is number of moles of solute upon the number of moles in the solution. So here N1 and N2 are the number of moles of solvent and solute respectively present in the solution. So for dilute solutions, N2 we can say, N1 we can say is much greater than N2. So we can basically neglect this N2. This N2 which is there, this can be neglected. So only we will be left with N2 upon N1. So P01 minus P1 upon P01 will be equal to N2 upon N1. Here now, or we can write it in the form of their masses and the molar masses relation. So we can write this equation as number of moles, weight or masses into the molar mass that is given. So W2 into W1 upon M2 into W1. So here W1 and W2 are the masses and M1 and M2 are the molar masses of solvent and solute that are present respectively. Now from this equation, knowing all other quantities, the molar mass of solute M2 can be calculated. So from here we can calculate the molar mass of the solute, that is M2. Now let's talk about the next property, that is the elevation of boiling point. The vapor pressure of a liquid increases with increase of the temperature. It boils at the temperature at which its vapor pressure is equal to the atmospheric pressure. So now what we are saying is that the vapor pressure which is the of the liquid, it will increase with increase in the temperature, okay, and it boils at the temperature at which the vapor pressure of the solution becomes equal to the atmospheric pressure. Atmospheric pressure is 1 atmosphere bar. So in that case, the vapor pressure of the solution should be around 1 atmosphere. For example, if we take water, it boils at 373.15 Kelvin, that is 100 degrees Celsius. Because now why it boils at this point? Because at this point the vapor pressure of water is around 1.013 bar, that is close to 1 atmosphere. Therefore it boils at this 100 degree Celsius. So we have also learned in the past section that vapor pressure of the solvent decreases in the presence of non-volatile solute. This we have already discussed above. So figure 1.7 depicts the variation of vapor pressure of pure solvent and solution as a function of temperature. For example, the vapor pressure of an aqueous solution of sucrose is less than 1.013 bar at 373.15 Kelvin. Now, in order to make this solution boil, its vapor pressure must be increased to 1.013 bar by raising the temperature above the boiling temperature of the pure solvent, that is water. Okay. Now, when we talked about water, what we had, the vapor pressure was 1.013. Now, you have added a sucrose content to the same water. Now, what will happen? Its vapor pressure will be less than 1.013. So in order to make the solution boil, what we will have to do? We will have to get the vapor pressure to 1.013 bar by raising the temperature above the boiling point of the pure solvent, that is water. So boiling point of water will cross over, it won't be 100 degree itself, it will cross it, and we will have to heat it more so that the solution of sucrose in water starts to boil. Thus the boiling point of solution is always higher than that of the boiling point of the pure solvent in which the solution is prepared. So now what we are saying is that from this we have understood that when we had just water, its boiling point was 100 degrees Celsius. Why? Because its vapor pressure was at 1.013. But on adding sucrose, what has happened? Its vapor pressure has reduced. So that means if its vapor pressure is reduced, its boiling point will increase more. So you have to heat it more so that its vapor pressure reaches to 1.013 bar. Similarly, to lowering of vapor pressure, the elevation of boiling point also depends on the number of solute molecules rather than their nature. So now if you want to lower the vapor pressure, we are saying that the elevation of boiling point, it depends on what? The number of solutes rather than the nature of the molecules that are present. Now a solution of 1 mole of sucrose in 1000 grams of water, it boils at 373.52 Kelvin at 1 atmospheric pressure. So let T naught B be the boiling point of the pure solvent. Say T naught B is the boiling point of water and TB be the boiling point of the solution. Once adding sucrose, it will be a new solution. So that is the boiling point at which the solution will boil. So the increase in the boiling point, that is delta TB, can be given as TB, that is boiling point of solution, minus T naught B, that is boiling point of the pure solvent. Now this is known as the elevation of boiling point. Experiments have shown that for dilute solutions, the elevation of the boiling point, that is delta TB, is directly proportional to the molar concentration of the solution of the solute in a solution. So what we are saying, through experiments we have found that for dilute solutions, the delta TB which is there, it is directly proportional to the molar concentration of the solute that is present in the solution. So we can write delta TB is directly proportional to M, that is the molar concentration of the solute in a solution. So now if we have delta TB, so this proportionality sign we can remove and we can put a constant, proportionality constant, that is Kb into M. Now here M is the molality, that is the number of moles of solute dissolved in 1 kg of solvent, and constant of proportionality, that is Kb, that is called as the boiling point elevation constant, or it is also known as the molar elevation constant. The unit of Kb here is Kelvin kg mole inverse. Now values of Kb for some common solvents are given in the table. If W 2 gram of solute of molar mass M2 is dissolved in W1 grams of solvent, then molality, that is M of the solution, can be given by this expression. So M equals to W2 upon M2 upon W1 divided by 1000. So that equals to 1000 into W2 upon M2 into W1. Now substituting the values of the molality in the equation, we can get that delta TB equals to Kb, that is the constant, into 1000 into W2 upon M2 into W1. So M2 can be given as 1000 into W2 into Kb upon delta TB into W1. So thus, in order to determine M2, molar mass of a solute known as the mass of solute in a known mass of solvent is taken and delta TB is determined experimentally for a known solvent whose Kb value is known. Okay, so that was it for today's video. We learned about two properties of the two colligative properties, that is relative lowering of vapor pressure and the elevation of the boiling point. In the next class we will continue with these properties and do the rest of the three properties. So thank you so much for watching today's video. Please don't forget to like, share and subscribe to the Bodhi Academy.